Greetings student. Today we will be discussing about the concept of moment of inertia. As we know the concept of moment of inertia, it is the second moment of the area. The basic prelude for this will be the centroidal moment, wherein we came to know that the centroid in the unit 4 of the elements of civil as the first moment of the area. Wherein we used to write it in the term of either as an integral or using the summation as ay or ax, which is the product of both of them. That was the first moment of the area. Now going with the moment of inertia, or in general which is also referred to as MOI, the moment of inertia is called as the second moment of the area. So in the second moment of the area, we will be discussing about the first moment of the area multiplied by the arm again. So that is ay multiplied by y, which is in general called as the ay square, or ax multiplied by x, which is called as the ax square. So here it is about the second order term which we will be seeing in the moment of inertia, because it is the second moment of the area. So going with the moment of inertia, let us try to understand the moment of inertia from a physical point of view. So let us take the example of this board here. So if we see in majority of the cases, if we see laborers carrying any heavy objects, etc., they never tend to carry it in this fashion. This fashion usually will tend to bend it more such that it is more vulnerable here. So it is always carried in this fashion. So this is one practical importance of moment of inertia, where they try to carry any object in this. So we will be discussing about the numerical aspect of the moment of inertia later. Just to know practically that you are trying to carry it along this axis and not about this axis because of the resistance offered by a material along this particular axis. So moment of inertia is basically can be termed as the rotational restraint provided by a member. So how is the rotational restraint is? We got to know that we actually carry a member along one particular axis, so it offers a particular restraint. So usually this has a very practical significance related to the civil engineering aspect, wherein we discuss about how a configuration of a section should lie or how a section should be placed, etc., owing to the basic concept of the moment of inertia. Let us come to know about the basic classification of moment of inertia now. The moment of inertia is usually classified into three types. The first part is what is called as the mass moment of inertia. In the mass moment of inertia, we are basically concerned with the centroid of gravity and the mass distribution of an object. So in the mass moment of inertia, basically we try to find out where the mass is placed and how it actually restrains the rotation action on a particular mass. The common expression given to the mass moment of inertia is given by m multiplied by the r square, where m is the mass of the cumulated mass of a body put up at a particular area, and r is the perpendicular of distance square from the reference point of measurement. So in this mr square, it is easy to know that the moment of inertia is more directly or proportional to the square of the radius or the perpendicular distance when compared to the mass. This can be clearly seen in case of ballerinas, where they are trying to rotate about a particular axis. If a ballerina is trying to make her rotation faster, she tries to come nearby. So she actually makes her body to contract more. That is where she tries to rotate fast. Whenever she actually expands her body to a larger extent, her rotation speed comes down. This is a practical example of moment of inertia, which is the mass moment of inertia. This is exactly useful in finding out how the configuration of a body will actually dictate its rotational resistance. So the same model with the same body weight there, based on whether she is contracting or expanding, the rotational moment of inertia changes there for the mass moment of inertia. There comes the second moment of inertia, which is the area moment of inertia. The area moment of inertia is nothing but the second moment of the area. Here we are concerned about the center of the centroid of the areas there. The centroid of the areas will be either the x bar or y bar, which we discussed in the previous section. There we are trying to find out area multiplied by the square of the centroidal distances, either the y distance or the x distance. The third moment of inertia is usually called as the polar moment of inertia. In the polar moment of inertia, it is actually concerned with a particular type of rotation wherein it does not happen about the individual longitudinal axis of the body. It is majorly constrained about the twisting action of the body. So here it is basically the rotation of a particular cross section of the areas, but here it is about the twisting of the axis. This can be particularly seen here, wherein if you are actually trying to rotate this about this axis, it is the areas which we are talking of. Whenever this is trying to be rotated like this is what is called as the polar moment of inertia. It is basically concerned about the twisting resistance offered by the body. So in line with all these basic classification, we can majoritarily come to know that since we spoke of the centroid in the previous unit, we will be discussing in relation to the syllabus, it is only about the area moment of the inertia. Okay, so area moment of inertia is where you will be trying to find out the corresponding centroidal distances and the area of the individual areas of a given composite shape, where you divide it into areas of known dimensions and properties along with the particular centroidal distances from the reference axis. You will be able to compute the area moment of inertia. Okay, we shall now proceed with the two important theorems related to the moment of inertia. One is called as the parallel axis theorem, and the other one is called as the perpendicular axis theorem. The basic aim of defining these two theorems is that when we are trying to find out the moment of inertia of a body, it is not essential that the reference axis coincides with the centroid of the whole given area. So in that case, we'll have to utilize certain theorems to find out the moment of inertia about an axis which is away from the centroidal axis of the given shape. In that case, we'll be using both of these theorems basically. Since we discussed about the polar moment of inertia, we'll first start with the perpendicular axis theorem. In the perpendicular axis theorem, here if we consider a three-dimensional space wherein the body is kept, and if the body is kept in one particular direction, here if we are trying to find out, since basically we know that the moment of inertia is the area multiplied by the distance square, there if we are trying to find out this distance, if this is an x and y coordinate of the distance which we are trying to, when we are trying to find out the moment of inertia about an axis which is perpendicular to the plane of the board here, the z direction is perpendicular to the plane of board, the distance is marked here as r. So we can say from the Pythagoras theorem that the r square here, which is the hypotenuse, will be equal to the x square plus y square. So here the polar moment of inertia will be equal to the area, which is the integral of dA into r square. And here this r square is nothing but the perpendicular distance of the area with respect to the reference axis. And with the Pythagoras theorem, we can substitute the integral of r square as x square plus y square into dA. And as discussed previously, and we know that whenever we have a distance of y, it is always the distance of the centroidal point of the individual shape from the x-axis, and the x distance is the centroidal distance of the individual point with respect to the y-axis. We'll just try to separate out these equations. So this becomes x square into dA plus integral of y square into dA. So here we can make out that since it is x square, it is always the rotation about the x-axis. We are defining it as a perpendicular distance. So this becomes Iyy, and since this is the distance from the x-axis, this becomes Ixx. So this establishes the basic proof that is required for the statement of the perpendicular axis theorem, from which we can say that if we need to find out the moment of inertia of a body about a perpendicular axis, we need to know about the axis, both the axis which is perpendicular to either of the axes. So here this is universally applicable for either of the axes. In case if you are trying to find out Iyy, which is perpendicular to both Ixx and Izz, the terms are interchangeable. Since we now consider as a distance which is perpendicular to the area which is placed in an xy axis, we can say that the Izz is equal to the sum of the moment of inertias in the plane where the area is kept, that is Ixx plus Iyy. Now we will discuss the parallel axis theorem, which is one of the very important theorems to solve the numericals and also obtain the basic expression for basic shapes in case of the moment of inertia. The statement of the parallel axis theorem states that in order to obtain the moment of inertia about a reference axis, for example here the moment of inertia about the reference axis will be Ixx. The moment of inertia of an area about a given reference axis will be equal to the sum of moment of inertia about the centroidal axis. That is, we usually represent the centroidal axis by using IgG plus, or the sum of, as I already mentioned, the sum of moment of inertia about the centroidal axis and the product of, here the product is inside the bracket, area of the individual shapes and square of the distance from the reference axis. So what we can know here is, in general, let us try to represent this in a pictorial format. So here if we consider one complex area of this fashion, and the centroidal axis will be passing through one particular distance here, and we want the moment of inertia about one particular reference axis which is away from the centroidal axis. But the important thing here is we need to note that both of these axes are parallel to one another. That is where it justifies the parallel axis theorem. So if this axis is situated at a distance of y, and if there is an elemental strip which we are actually considering here, and the elemental strip is situated at a distance of h, so what this theorem actually means is, as I mentioned, it is the sum of different terms there. So here the I, which is the reference axis IXX, and IGG, this is for the GG axis here. So the IXX and IGG are basically the centroidal axis and also the axis at the reference at the base. So here the IXX will be equal to IGG, which is the moment of inertia about the centroidal axis, plus, as I mentioned, the area of the individual shape which is inside the figure. This is actually important because whenever there is a complex shape, in order to reduce the complexity, we divide it into areas of known dimensions and shapes. And this perpendicular distance here will be equal to h plus y the whole square. So that is the statement of the parallel axis theorem. In general, we may also go with just finding out the distance because we first established the centroidal axis. In line with the diagram here, for which we will be following with a derivation to obtain this. This is a statement wherein we will actually obtain the final expression, but this statement which is quoted is with reference to this diagram given here. We shall now proceed with the proof of the parallel axis theorem. We established the relation for the parallel axis theorem as IXX is equal to IGG plus A into, in this corresponding figure, it is equal to h plus y the whole square. Again here this distance depends because we are considering an elemental strip at a distance h from the reference axis. Again, this term is variable based on the numerical problem and its nature. So here let us try to obtain this expression. What happens is, whenever we are trying to find out the elemental strip, the moment of inertia there, since this is the second moment of the area, we will be writing this as integral dA multiplied by the perpendicular distance h plus y the whole square. So here what happens, this is analogous to relation of a plus b the whole square. So here we will be splitting this term as dA into h square plus 2hy plus y square. So this is the split of the h plus y the whole square term here. So upon rearranging of the terms here, let us try to rearrange for the summation of each of the terms here. So this becomes integral h square into dA plus integral of 2hy into dA plus integral of y square into dA. So here if we observe these terms, it is basically the area multiplied by the square and also the area multiplied by the term here. So we need to make a careful examination here. From the basic assumption of the centroid, we know that here, upon rearranging of the terms, we know that here we are taking out h square outside integral dA plus 2h outside integral y dA, and this is plus integral of y square into dA. So here we know that the first moment of the area about the centroid is equal to 0. So going with simplification of this term here, this h square dA is nothing but the moment of inertia of the elemental strip about the centroidal axis. So here we can write this as I of GG. And since the second term here is 0, we will proceed with the third term. So integral of y square dA, taking out y square outside, integral of dA will be equal to A, since you are integrating the whole elemental strip for the area. So this gives us the final expression for IXX, which is the moment of inertia about this area about an axis parallel to the centroidal axis, away from the centroidal axis a distance y, as IXX is equal to IGG, which is the moment of inertia of the area about the centroidal axis plus the area of the whole strip multiplied by the y square, where y square is the perpendicular distance between the two parallel axes. So this establishes the proof of the parallel axis theorem. So from the final line of the theorem, what we can make out is the IXX, which is the moment of inertia about any area at an axis which is parallel to the centroidal axis. This may not be any convention which is permanent here. IXX is just a representation of an axis which is parallel to the centroidal axis, is equal to the sum of two terms, where this IGG is nothing but the moment of inertia of the given shape about its own centroidal axis, plus the area where this area represents the individual area of the subsection multiplied by the square of the distance. This y square is again not a universal constant here. This y square just represents the perpendicular distance between the two parallel axes. There the parallel axis represents the axis which is passing through the center of the individual area and the reference axis. So this is the square of that distance which is computed for each of the shapes in the subsections. So this is just a general expression where no terms are universal constants. Let us now discuss the concept of radius of gyration. As explained in the classification of moment of inertia, we discussed briefly on the concept of mass moment of inertia, wherein we discussed that in case of the ballerina who stretches her body and contracts her body, The stretching of the body will actually ensure that her rotation speed actually varies with respect how when it is contracted. From which we came to know that the effect of a particular term, which is in a quadratic form, has an effect on the rotational restraint offered for a body, having the mass being constant. So in case of the mass moment of inertia, the radius of gyration refers to a particular distance to which the mass has to be kept, wherein to maintain the same moment of inertia at what distance relatively to the before case. So on the same lines, it is about the net effect of the rotational reason that is caused by a particular distance or a perpendicular distance from the body in case of the mass moment of inertia. Coming to the area moment of inertia, where we are discussing the radius of gyration. In case of the area moment of inertia, the important concept is that we are actually trying to divide the whole area into an elemental strip and keep it at one particular distance such that the whole effect of the rotational restraint of the area is actually given by that particular strip. So what happens is, if you are actually having a very large amount of area, you are trying to convert this area into a very small strip. The distance at which this area is supposed to be kept from the reference point to obtain the same rotational action as the original area is what is called as the radius of gyration. So the radius of gyration is usually given by the form that if the moment of inertia is equal to I, the radius of gyration will be equal to A into K square. Here, this K represents nothing but the distance at which the body is supposed to be kept for the same elemental strip to give the same rotational action. So here we are concerned about finding out at what distance it is supposed to be for the elemental strip to obtain the same rotational effect as the initial case. So here, if we write the expression in terms of Ixx, it will be equal to A into Kxx square, where the term of Kxx square corresponds to the radius of gyration about the x-axis. So in order to obtain the term of Kxx, that will be equal to root of Ixx by A, where the Ixx was the initial moment of inertia divided by the area of the corresponding section will give us the radius of gyration. Similarly, if we require the radius of gyration about the yy axis, this will be equal to root of Iyy, where the yy is the moment of inertia of the area about the yy axis and the area correspondingly. So here it is nothing but obtaining the root of the division of the moment of inertia divided by the corresponding areas to obtain the corresponding radius of gyration about its respective axis.